energetic reactions. So let's keep track of the energetics of chemical reactions, and we'll do that in a subject called thermodynamics. Thermodynamics involves heat transfer and tracking of the energy of systems and surroundings. When we work in thermodynamics, we'll define a system and say, okay, everything that happens in this beaker will be the system, everything else will be the surroundings. And we'll track how heat moves between the system and the surroundings. Now, energy, and I'll use the symbol E, is going to change in these systems, and energy will change by two mechanisms, heat and work. I'll use the symbol Q for heat and the symbol W for work. Now, it's important that we understand the difference between energy, heat, and work. Energy is a quantity that a system can contain, and energy can be used to do work or transfer heat. Heat and work are mechanisms by which energy is transferred. Energy is something you can have. Heat and work are mechanisms for transferring energy between the system and the surroundings. Let's look at how that works. Say heat, which I give the symbol Q, if that leaves the system, that would tend to lower the energy of the system. So we give heat that leaves the system the negative sign. We call that exothermic, heat that leaves the system. A negative sign allows us to use this equation naturally. That is, a negative heat naturally lowers the energy of the system. If heat's absorbed by the system, that's an endothermic process, heat going into the system, and we give that heat a positive sign. That positive sign says that raises the internal energy of the system. And we'll do a similar thing for work. If the system does work, we'll give that work a negative sign. That is, it takes some of your energy to do work. That's kind of a natural thing that you might already understand. If some of your energy is used to do work, then that should lower your internal energy, and we'll give that work a negative sign. Conversely, if you do work on a system, or if the surroundings compress a gas, that's work done on the system, and that raises the internal energy of the system. So this energy that we're talking about has two important properties. It's a state function and it's conserved. By conserved, we mean energy isn't lost or created. If it goes from the system to the surroundings, it goes joule for joule. So the energy of the universe, that is the total changes in the system and the surroundings, that always sums to zero. The amount of energy in the universe is constant, and all I can do is move it from one system to another, or from the system to the surroundings. And I do that with heat and work. Energy is a state function, and that means it depends only on the initial and final states of the system, not on the path to get there. That is, if I'm at the top of a hill and I jump down to the bottom of the hill, my gravitational potential energy changes. I have more potential energy here than I do here. And that doesn't matter if I jump off the hill directly, or if I run down the hill in circles, or if I fly up in the air and then come down to the bottom of the hill. If I start here and I end here, the energy change, that difference is always the same. But the work I do to get from here to here might be different. So work and heat are not state functions. They depend on the path you take, but the energy change is a state function. Energy is a state function, it's conserved, and when energy is moved from a system to the surroundings, it's moved joule for joule. If I do a joule of work on the surroundings, I lose a joule of work. If a joule of heat is absorbed by me from the surroundings, that's joule for joule. The surroundings lose a joule of heat, I gain a joule of heat. That's the essence of the first law of thermodynamics.